Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about circuits that have inductors and capacitors present as a series circuit. So basically a loop with an inductor and a capacitor in it. Specifically we're wanting to look at a few graphs that we might associate with these. And of course there's a lot more than I can do in a simple, let's say 15-ish minute video. So I'm giving you some of the highlights of it and maybe some ideas that you can go explore on your own. Before we do all that, it's worth recalling what it is that we're talking about here. It's an LC circuit. That means we have a circuit that has a capacitor and an inductor in series. This could be actually a whole set of capacitors and a whole set of inductors as long as it's reducible to an equivalent capacitor and an equivalent inductor. The capacitor has capacitance C, the inductor has an inductance L, and we also assume that initially the capacitor is charged up, and so we ask what will happen. Now in a previous video I discussed this in terms of the loop rule and the equations that describe voltage drops for the capacitor and for the inductor. And so of course, like, the loop rule says that the voltage drop on the capacitor and the voltage drop on the inductor must have equal magnitude but opposite sign. So that's that. Beyond that, I could maybe graph also the current in the inductor, which should also tell us what the rate change of the charge on the capacitor is. And I could also, in principle, plot things like the total energy stored in each one of these two elements. Some operative equations that we maybe need to recall is that for the capacitor, delta Vc should look like the charge stored divided by C. For the inductor, delta VL should look like negative of the inductance times the rate change of the current present. It's actually technically an average value, but be that as it may. If you are using the actual rate change, then you're going to get the right answer instantaneously. And then maybe it's also worth recalling what the potential energies are for each of these. So for a capacitor, should look like 1/2 of the charge squared divided by the capacitance. For the inductor, it should look like 1/2 of the inductance times the current squared. And maybe one more relevant equation. We expected that omega squared for this system, which by definition is 2 pi squared, or 2 squared pi squared over the period squared, should look like 1 divided by L times C. So those are kind of our relevant equations off the start. So with these preliminaries aside, let's go to the simulation, which is of course in Octave. This basically is the simple code that I've written up for this simulation. You can sort of like write it down off of this video if you want, and write this yourself if you'd like. You may have to pause it a few times in order to get everything. As always, there's certain parts of this code that are more important than others. You don't have to write like all the comments and all that. But the basics of what this thing is doing, if you look at it, first of all, I have to give it some parameters. The parameters that I've chosen to give it are a defined period in seconds and a defined capacitance value in farads, and then also a maximum value for the initial capacitor voltage, and ergo also for the voltage on the inductor, albeit with an opposite sign. Everything else is from there basically calculated. So the time step is just to get some idea of like how many points do I want in my plots. Essentially, like the smaller this is, the more points I'm going to have. The max value basically is like over what range of times do I want the plot to look. This t parameter is just calculating time. And then I also have a maximum energy value, which is of course calculated as per the equation that I've written here for the maximum potential energy of the capacitor. Q squared over C is also, for what it's worth, is 1/2 times C times delta V squared for the capacitor. So that's in terms of the code parameters. Then I've set it up so that there are several different types of plot that can be generated. We could do the voltage for the capacitor, we could do potential energy for either of the capacitor or the inductor, we could do the charge on the capacitor, and we could do the current in the inductor. And so you choose which one of those you want, and then the rest of this code is basically just for it to output one of those graph types or display a message saying you've got to choose one of these graph types. So let's run it and see what we get. This right here is the capacitor voltage versus time for this LC circuit that I've set up with the parameters defined as I did there. I'm just going to stick it into my presentation, and the reason why I'm putting it here is because I want to go and also kind of compare it to the other possible graphs that I can get off of here. So for example, potential energy on the capacitor would be a type 1 graph. So I'm going to do that, and here's that graph. Let's copy it to the clipboard. Let's throw this over here. So here's the side-by-side of those. Maybe I will also have a side-by-side of that and the energy from the inductor, and then I also want maybe each of the other two graphs that we could do. So let's quickly get those other two. So let's do energy for the inductor, which looks like this. Let's copy that over side by side, and then let's actually also have one that shows the charge from the capacitor, and let's also maybe have one that shows the current on the inductor side by side with the voltage drop, with the energy, excuse me, of the inductor. So that would be type 3 for the charge. So copy that, go over here. I wanted to do charge, and I wanted to do energy for the capacitor. I also really wanted to do charge and voltage for the capacitor side by side. So we could look at those. And then I got a whole lot of charge apparently stored on this capacitor. I think it's supposed to be in millicoulombs. And then last but not least, let's do type 4, which was the current in the inductor, just to get a graph of that. So here's the current in the inductor, and I wanted to put that one side by side with this one, and let's actually do it side by side with the charge stored as well, just for the variety. So here it is with the charge stored side by side. All right. So right now I've kind of got all the graphs that I could. The only thing I can do differently at this point would be changing parameters and looking at what they do. I really wanted to just kind of briefly compare and contrast them. So here's for both of these is the capacitor. This one is voltage, this one is energy. What you should notice, or most prominently notice, is that there's more oscillations here than there are here. In fact, if we count them, in both cases we're starting at a peak, so 1, 2, 3, 4 oscillations in 100 milliseconds. In the same 100 milliseconds, 1, 2, 3, 4, 5, 6, 7, 8. So if we want to get the period of oscillation, we divide that time by the number of oscillations. And so this would be 25 milliseconds, or in other words 0.025 seconds. This one would actually be 12.5 milliseconds. If we go back to the code, by the way, that 25 milliseconds, 0.025 seconds should be familiar because it's what we set the period as here in the code. So that's kind of confirmation that it's doing what we expect it to do. So first result, though, that we're getting here is that the energy has half the period as the voltage. Now you may be wondering why that is. By the way, this also means the frequency for the energy is twice that of the voltage frequency. And it comes out of a trig identity that basically says that the cosine squared of an angle is equal to essentially like a 2 minus the cosine of twice the angle over 2. And essentially that's a trig identity. Note that in one case you have cosine squared, in the other case you have cosine of 2 times the angle. That is akin to saying that you have cosine of twice as much frequency. And the cosine squared is coming from the fact that you have a cosine here, and that this one right here, the energy versus time, should look like the square of the voltage versus time multiplied by the capacitance. So you expect there to be double the frequency for the energy as for the capacitance. Same thing is true, by the way, if you were to go down here and compare for the inductor the energy versus time and the energy and the current versus time, since energy goes like current squared. Note that the other important factor is that the energy bottoms out at 0 in both cases, whereas the voltage drop in the current can be both positive or negative. Second thing to note is that we have the same frequency for both the charge and the voltage and also the current. We might express that by using charge, voltage drop, and current as subscripts for the period. And again, if I were to go down here to the charge and the inductor current, same thing. Period is still the same, albeit everything is kind of shifted in phase by a quarter cycle because we're starting from 0, and so 1 whole cycle gets us back to 0, 2 whole cycles back to 0, 3 whole cycles back to 0, 4 whole cycles back to 0, whereas we were looking at peaks with the other two graphs. Okay, what else can we get from these? Well, the other thing that we should be able to get off of this graph is if we know what the capacitance is, we should be able to get the inductance and vice versa. So how does that work? Well, we know that the period was 0.025 seconds. We also know from looking at the code that this is the capacitance. We know that omega squared, which is 4 pi squared over t squared, is 1 over LC. It follows that the inductance L must look like t squared, the period squared, divided by 4 pi squared times C. So we can plug in numbers and get the inductance. So in this case, these are the numbers that we would be plugging in. You can throw that into your calculator. What you'd end up getting is 0.042217. So let's call this 0.042 henries. Other thing that you can get off of this, by the way, is the initial value, which seems to be about 12 volts, initial value for voltage. As a quick check of this, And as a quick check of everything else here, this right here was 12 volts was our maximum. So delta V C naught is 12 volts. This also means we could figure out what the initial charge is. You know that Q naught should be C times delta V C naught. And so that ends up basically being 12 volts times 0.00375 farads. So multiply those two things together and you get the initial charge, which was 0.0045 coulombs. So if we go back and look at our charge versus time graph, for example right here, we can see that 0.0045 is a reasonable estimate for what that graph is suggesting. And we could also go through and rerun it here if we prefer, and same thing. So again, if I'm looking at this graph right here, this value is essentially my Q naught value. And on a similar note, this value is my I naught or I max value. We can go and double check some of these claims by changing some of the relevant parameters in the simulation and replotting. So this right here is sort of like our initial set where we had 12 volts, 0.025 second period, and 0.00375 coulomb. Alright, so if we double the period from 0.025 seconds to 0.05 seconds and run the simulation again, then what we're expecting to see is for 4 of these periods to, rather than taking 100 milliseconds, take 200 milliseconds. And that is indeed what we are now seeing here. Here's the plot, and here it is pasted onto the little share area. So doubling the period causes us to double the number of time to get the same number of periods. It also gives us still the same value for delta V max. We don't have any way directly of seeing what the value of C is, but since we fixed C and changed the period, we expect for L to change. And if L changes, that means that we expect the value of the current to change. So we expect kind of for the maximum value of the energy to remain the same as before. So let's do a quick check of that. We'll do potential energy for the inductor, which I pull up. Here's our energy stored in the inductor. This is between 0.025 and 0.03. If we were to look at our originals here, inductor energy between 0.025 and 0.03, so that hasn't really changed. The period of this thing has changed. Again, it takes 200 milliseconds to get to 8 oscillations rather than 100. And if we were to look at the current, we expect that the current value will have changed because we expect the inductor's value to have changed. So let's pull open the current versus time, which is number 4. So let's do type 4 graph. Click. All right, here's the current versus time. Look at the peak value of current. We could call that like 0.014 something, roughly. And if we come back over here, originally the current was only making it to, or was making it all the way to 0.02 something. So we've roughly halved the amount of current present here in order to keep everything else equal. Okay, let's go back. Let's change our value of the period back to what it was initially, and this time let's change the capacitance value. So here's the here's this again. Let's go back to graph type 0. Let's change the capacitance value to, let's say, 0.0075. So we're doubling the capacitance rather than the period. Let's again do this thing. Okay, notice that the capacitor voltage versus time graph is unchanged compared to what happened when we doubled the period, or compared to what we had before we doubled the capacitance. Okay. However, if we look at other things like the energy graph, so let's change this to charge stored maybe, or potential energy. We'll do potential energy here. Potential energy should be different. Okay, so our maximum value is between 0.05 and 0.06, whereas before it was between 0.025 and 0.03. So we basically doubled the energy, and since energy looks like C delta V squared, and we haven't changed delta V, we therefore would expect this energy to double. We also expect there to be a change in the current, although that one's going to be harder to see with this simulation because I've changed two things by changing the capacitance. One is that the period, the inductance has changed as a result of the period being the same but the capacitance being different, and then the energy maybe has changed as a result of the capacitance being different. But on the current graph, if you're calculating it from energy as this simulation is, there's kind of two changes that have happened, one being the inductance and the other being the energy. So coming back here, let's look at the current versus time graph, which is graph type 4. And let's see if this is recognizable. So here it is, the current in the inductor versus time. If we go back and look at the original, we've basically doubled the maximum value of the current. And again, that's because we've made a couple changes. One being the capacitance, which in our code means the inductance has changed. In an actual circuit, what would have actually changed is the period. And the other one being how much energy is being stored. So that one's a little bit harder to get. One last thing, which is, let's look at what happens if all we do is just double the voltage. And I'm only going to look at the capacitor graph. So here's 12 volts maximum voltage. Let's go back in here. Let's change this back to the way that it was before so that we have only one variable changing at a time. Let's change the Vmax from 12 to, let's say, 14. And what we should see is that the new Vmax is a little bit higher than the old Vmax. Oops, got to get the right graph again though, which is graph 0. Alright, so now notice that we're much nearer to 15 than we were when we were at 12. And if I were to change this instead of to 14 to, like, let's say 24, so I've made a true doubling, then here's 20, here's 30, we're somewhere between 20 and 30, this is roughly 24. And so let's put that in here. Oh, seems to have changed size though. Maybe one last comparison, which is what happens to the energy stored. So here's my stored energy. Let's copy this guy and go paste it side by side. Notice that the maximum value of energy stored has changed here. It's roughly, and in fact we know exactly, 4 times higher than before. Because again, we expect for energy maximum, we could call this U naught, to look like 1/2 C delta V naught squared. So if I've doubled this number, I square it, that means I've quadrupled this number. And so my maximum here is about 4 times, or is 4 times my maximum here. There's many other changes you could be making here. I've done more than you probably wanted to see, but hopefully you've learned a little something from these graph simulations, maybe a little bit about how to interpret the graphs, maybe a little bit about how changing one thing changes the other, and what parameters do what. In any case, thanks for watching.